So in this part, we'll see more examples of SN1 versus SN2, and perhaps we'll elaborate a little more on the factors that we have looked at to compare the two mechanisms. So here's an example of a methyl X reacting with a strong nucleophile. And the fact it's a methyl X, automatically we're going to label it an SN2 reaction. And we know already that the mechanism is going to go through a concerted pathway. That's why the nucleophile is going to come from the backside of the leaving group, giving you the inversion of configuration structure. Stereochemistry wise, this compound is achiral, but it's always good to actually write the structure in a way that we acknowledge the inversion of configuration aspect of this mechanism. So we could see clearly here that the transition state that we usually observe in the SN2 mechanism. And again, this transition state is being speculated, it's not being confirmed. It is speculated, and that's the difference between a transition state and an intermediate. This is basically telling us how we can utilize SN2 to produce a lot of useful compounds. Just changing the nucleophile will take me from an alkyl X to an alkyl iodide to an alcohol to an ether to a thiol to a thioether to an ammonium salt to an azide to an alkyne to a nitrile. You could see here also you could make an ester using the carboxylate attacking alkyl X. That will give me an ester or a phosphonium salt that we're going to actually see in one of the reactions of the alkene chapter. So this basically gives us a hint of how useful the SN2 reaction actually when it comes to organic synthesis. This tells us ranking of nucleophiles. And it's very important that we differentiate between nucleophilicity and basicity. I mentioned this previously. All strong bases are strong nucleophiles, but not all strong nucleophiles are basic. And here's an example. I'm just going to use two. Phosphorus is the best nucleophile we can use in organic chemistry. I- is a stronger nucleophile than RO-, even though HI is a stronger acid than alcohol, meaning I- is a weaker base than alkoxide. And the weaker the base, it doesn't mean the less nucleophilic it is. Why? Because there is a difference between nucleophilicity and basicity. Basicity has to do with abstracting a hydrogen from an acid. Nucleophilicity has to do with how the atomic size of the atom. So if I take fluoride versus iodide, the bigger the atomic size, the softer it is. And when it is a softer atom, it easily overlaps with the back loop of the CX in the alkyl halide structure. And that's what helps in the formation of the nucleophilic substitution product. So the more polarizable, the bigger the atomic size, the softer it is as a nucleophile. And the softer it is, the faster it will form it will overlap with the back loop of the carbon empty orbital, and that will basically help in the formation of the nucleophilic substitution reaction. And that's important to keep in mind, that nucleophilicity has nothing to do with basicity. And for us to run SN1 or SN2, we care about having good nucleophiles, not good bases, even though all strong bases happen to be strong nucleophiles. So here's the phosphorus is better than an amide. NH2- is an amide. S-, that's the negatively charged sulfide. Here's the I-, here's the acetylide, an ion. Here the CN-, the cyano. Here's the neutral amine. The neutral amine, when it's a tertiary, it's better nucleophile than the alkoxide due to the atomic size of the nitrogen. It's much bigger than oxygen, even though oxygen is negatively charged. So that's important to keep in mind. Here's the list of moderate, and here's the list of weak nucleophile. Here, familiarize yourself with these. It's important that we are able to also rank them, because you may be asked the question, which of the following is a strong nucleophile? Or you may be asked the question, rank the following nucleophiles. So that's important to be task to be able to do it, is to familiarize yourself with all of these examples. So as I mentioned, the base will be looking for a hydrogen to be abstracted, while the nucleophile will be looking for an easy access to overlap with the empty orbital of that carbon that's going to attack. We've seen this already. The solvent effect, polar versus polar product versus polar A product. So that's important to keep in mind. Here's the examples of leaving groups. So we got the halides, we got the sulfonates. So this is the tosylate. So if I have a tosylate, R-O-T-O-S, what is that supposed to mean? What it means, it's an R-O sulfonate group. So the toluene sulfonyl oxygen is basically having a toluene sitting on this R group and a sulfonate that will be the tosylate structure. I could have a sulfate, I could have a phosphate. So all of these are examples of leaving groups that are good leaving groups due to the fact that they are weak bases and very polarizable, highly polarizable. It's important to keep in mind also the reaction rate when it comes to SN2 versus SN1. SN2, we say the methyl X is faster than a primary than a secondary, where the tertiary doesn't happen in those mechanisms. And we've seen the reaction relative rate and the justification for it, the mechanism approach. We've seen the SN1, how the mechanism is. Here's an example for tertiary alkyl halide. The fact that it's a tertiary alkyl halide, I will predict right away that's going to go through SN1. What would that be? The very first step in the SN1 would be the formation of the carbocation. So you will end up making the carbocation. This carbocation is a tertiary carbocation. It's not going to go through rearrangement due to the fact that there is a primary and a secondary on the adjacent carbons, so they cannot be more substituted than this. Therefore, this carbocation will undergo the nucleophilic attack next to basically be giving you the SN1 outcome. So in this case, alcohol is being the nucleophile. Oxygen will attack the carbon. It still has a hydrogen attached, so that's why it's positively charged. Something else will take care of this hydrogen by basically having another alcohol picking up the hydrogen, or you could use the I- to pick up the hydrogen to give you the ether structure. So that's important to keep in mind. So you could basically go through this step in order for you to get rid of the hydrogen. So the methanol will basically pull up the hydrogen from this protonated ether to give you finally the SN1 outcome, which is the ether structure. So this is an example where an SN1 mechanism can actually take place. The reaction rate when it comes to SN1, tertiary is faster than a secondary, faster than a primary, but prior to that, I would be adding the benzylic and the allylic. So these are important to acknowledge that they exist. So the benzylic halide will be faster than an allylic halide, faster than a tertiary halide, than a secondary halide. Primary halide and methyl X, they rare to exist to go through an SN1 mechanism. We've seen the two factors that affect carbocations. We also seen the solvent effect, whether we use polar product or polar A product. So that's important to keep in mind. You can here see an example of a carbocation that will undergo nucleophilic attack to give you inversion of configuration and retention of configuration. You can see here slightly higher when it comes to the inversion, but again, they're almost considered to be a racemic mixture. This is an example of rearrangement. We've seen that in a previous PowerPoint slide, but let's look at this one. So let's say I have this structure as an alkyl halide, and this carbon happened to have a more substituted carbon next to it. That's a tertiary carbon. So what's going to happen, that there is a methanide shift to be expected to give you the carbocation on the tertiary carbon instead. So why would this one go through the SN2 and just get it over with? Well, when you have a tertiary carbocation, it's always going to be faster to give you the SN product, which is going to be SN1 in this case. So the reason behind rearrangement It's always just to give you more stable carbocation to lower the activation energy for the following step. That's why it's important to do the rearrangement if it's possible. Do not look beyond the adjacent carbon, because the rearrangement will not take place if it's a more substituted carbon further than the adjacent carbon. And it's important that we remind ourselves of those main differences between SN1 and SN2.